Okay, let's go ahead and get started. We've got a little bit of stuff to get through today, so we're going to go ahead and get started on that. Today's topic is going to be essentially programming game servers using TCPIP. And this is something that there are frameworks that do some of this for you, but I want to take a look at kind of a lower level thing. If we wanted to write our own game server and have complete control over it, this would probably be a good starting point with what we're going to cover today. Now, clearly, there are some things that we'll get into more complex views later on, but right now let's just go and get through kind of this introductory version of game servers. And we're starting to run out of time in the class. It would really be nice to have a few more weeks here to get some real work done in this. But we're going to get through this. So let's go and get started with game servers. Okay, so the idea here is before we get into the actual game server code specifically, there's a couple things. So far, we've talked about TCP/IP programming is using TCP. And TCP versus UDP is something we should talk about here when we talk about game servers. So TCP is kind of the sequenced, reliable transfer, but it can be slow. And really, slow isn't the right word. It's more unresponsive. It can have high latencies to get data through a TCP connection. So UDP is kind of a lower level protocol that doesn't have sequencing. It doesn't guarantee reliability. But because it doesn't do that, it can be very responsive and fast. So it's unreliable, unsequenced, but has the potential to be much faster than TCP. And the reason being that it all comes down to both of them are using IP addressed packets, datagrams that are routed through the internet. But the difference is TCP has this other kind of layer of processing that has to happen. When the packets come in, it has to make sure they're in the right order, it has to send a response back saying, yes, I got those correctly, and then more will come through and it'll acknowledge those. So this extra layer of processing that includes timeouts and acknowledges, adds a layer of kind of latency that we might not want in a game. So let's look at each of those two things in more detail. All right, so first off, TCP manages the idea of a connection. You say open a connection, it says the connection is open. You put data in a stream, it guarantees that the order that the data comes out is the order that they were put in. And it also guarantees that if it says it was sent, it knows 100% that it was received on the other end. So that kind of guaranteeing reliability and sequence order is part of TCP's job. And so in other words, it automatically will take a stream of data, divide it up into the datagrams, put them back together on the other end. It'll adjust the connection speed by changing the window size automatically to allow for faster or slower connections to push the data through. And we can use it using the send function, the receive function, to reliably transfer data from one end of the connection to the other. Now, all of that reliability stuff sounds great, but the part that it comes at a cost of is this reliability and the sequencing take processing power and time, and just the way the protocol itself was created can make that unsuitable for certain kinds of game interactions. Now, UDP doesn't have the idea of connections at all. It just is like a postal system. It's just sending datagrams. There's no guarantee that they'll be delivered or that the order that they're sent will match the order they're received. So if you send 3 datagrams, one right after the other, they might be received in a different order. They might come in a different order. Also, you might have duplicated datagrams. Also, there's no stream. We just send individual messages as datagrams. There's no adjustment for connection speed, so we have to do that ourselves if we want something that has some sort of flow control built in. Also, if their messages get lost, it doesn't tell us. It just basically silently they fail. There's no delivery sequencing, and duplicates can be received. You can send one packet. On the other end, you could receive 2 duplicates of the same thing. We should probably also add our own checksum or check value validation for any data that goes through there. But the main idea here, it's unreliable, unsequenced, but it doesn't have the overhead that we have with TCP or the latency. Now let's look at that. So given all that, TCP does definitely seem like the easier of the two options. But the problem is that TCP will kind of queue data until in other words, if you say send this byte, it won't immediately make a packet with just one byte. It'll wait until we get enough data or a certain amount of data to build up, and then it'll send the whole thing, because that's in the long run more efficient when you're dealing with a stream. Problem with that, though, is that we might want to send the data quickly and not have it wait. So we can turn that off. There's a flag we can configure a TCP connection with TCP no delay, which means that as soon as you get data, make a packet and send it through the transport. Now that's less efficient bandwidth-wise, but it can lower latency. But even with that turned off, TCP can be slow, because the way that it knows if a packet is missing, it just waits a certain amount of time, and then it will say, hey, if I didn't get an acknowledgement, I'll just resend that data that I already sent. So the idea there is that that can take time for the automatic resend to be triggered. And the delay latency could be 1/4 of a second for a resend. It could be worse if the kind of packet that gets resent gets lost too. In other words, you could have latency that ends up being 1/2 a second or even more. And if you think about a game with fast-paced action where you want to click and you want to fire a weapon and see what happens on the other end instantly, 1/2 a second can be, if we want a game that runs at any kind of frame rate, 2 frames a second really isn't going to cut it. So the latency being 1/2 a second or more makes TCP pretty much not usable for internet-based games. Now, if you have like a turn-based game or something like that, where you decide what your action is going to be, you click that you're done with your turn, TCP can work fine. TCP can also be great for sending like files from one machine to the other. Like here's a level, the next level, here's textures, here's skins, here are sounds for the next level. So kind of the game assets, TCP can be a perfect choice for those, because those would happen before the level starts. But real-time data for who fired when and at who and who targeted who and where the bullets are in the game as they're moving around, TCP is pretty terrible for that. Real-time data, it's just the inherent latencies and the built-in kind of back and forth needed for the kind of automatic resend logic, that we'd have no control over how any of that works. It all happens in the TCP layer. So what we're going to do is we're going to use UDP, and we kind of have to for a multiplayer game, because we need to have a quick response or the game is not going to be playable. And so we're still going to use kind of a client-server architecture, but it's going to be based on these like smaller, lower-level datagram concepts rather than a connection. Now, there are some other advantages to datagrams too, besides the quickness, and that is that notice with TCP we have a stream, and we don't really know when one packet ended and the next one started. It's just data coming out of a stream. Think of it like water coming out of a fire hose. But the nice thing about UDP is the data comes in defined packets. When it says I received a packet, I know think of that rather than a fire hose of water. Think of that as like a bucket of water. And that bucket that comes in, we can organize that to be game state information comes in for every bucket. Where if we did it through a stream, we'd have to add our own delimiters or our own way of knowing this is a group, this is the next group in the stream, next group in the stream. We're here, it's naturally with UDP organized into these kind of chunks of data that come in. All right, so what do we want? We want to have quick updates of inputs from players. We want to have the server update the game state based upon those inputs from the players. And then we want to have the server send out the updated game state back to the clients. And then the clients are going to use that to render the screen and then kind of repeat that process. Get input, send it to the server updates, here's where everything is in the game world, sends that out to the clients then render that to the screen and go back to the top and get more input. Now, that sounds great, but UDP is going to require us to do some think some things through, and it's also going to require us to program around those shortcomings of not reliable. We're also going to have to kind of program around the lack of sequencing or the possibility of duplicated messages. So we're going to have to be careful with how we use UDP because of the way that it works. Okay, So before we get too much further, let's look at a UDP data structure, datagram structure. So UDP datagrams, much simpler than TCP datagrams. Remember, a TCP header had 20 bytes, and it had all these things about window sizes, and it had sequence numbers and things like that. We don't have any of that with TCP. Basically, we have this 8-byte header that looks like this. It still has a port, and both a source port and destination port. And then it has this 16-bit length for how much data is in the payload, and then this 16-bit checksum. So the idea here, it's really simple. That all we have is, here's the port that it came from, here's the port it's going to, here's how much data there is, here's the checksum of that data, and here's the actual data. So this data that's down in here, since that's a 16-bit length, the maximum size that it could be would be that we could represent in that 16-bit length is 65,535. So essentially 2 to the 16 minus 1, 65,535. And that 65,535, though, we can't really get that much data because the largest packet size that we can have is 65,535, but that has to include this 8-byte header here and the 20-byte IP header that's going to go around that to make actual datagrams out of this to be sent. So we can really only get a size of 65,507 bytes worth of application data there. Now, as we're going to see, we probably don't really want payload sizes that big anyway, but just note that that's the hard limit on the size of a UDP datagram that we could ever send, is at 65,507 of application data, 65,535 bytes total. Now, I said we probably don't want to use datagrams that large because they can be problematic. So why? And the reason for that is that Ethernet really, which is kind of the lower level below IP, can't really handle datagrams that size. And since they can't really handle datagrams that size in a single packet frame, IP has to fragment those datagrams into multiple kind of lower level packets and then reassemble them on its own. But it doesn't do the reassembly the way that TCP does, where it guarantees reliability. And so let's take a look at how that fragmentation happens. All right, so if we have a MTU is kind of a maximum transmission unit. So in other words, that's the biggest size of a physical packet we could create. And Ethernet version 2 is 1,500 bytes. In some implementations of Ethernet, it's 1,492, but it's close to 1,500. And Wi-Fi, it's closer to 3,000, 2,900 and something. But note that Ethernet is widely used in networks, so 1,500 is probably a good number to stick to. So if we take a 3,000 byte UDP datagram and we want to send that UDP datagram that's 3,000 bytes, that won't all fit into one Ethernet packet. So what it has to do is IP has to divide it up into these smaller fragments. So the way it does that is adds the IP header on the front. Here's the UDP header, or 4 bytes of that. Actually, that should be 8 bytes. This is wrong. That should be 8. And then this is how much data we can have in the first fragment. So in other words, this plus that needs to add up to be less than 1,500. So 72, 82, 92, 93, 94, 95, 96. So this number is right, that number is right, that should just say 8 bytes. And I'll fix that in the slides before I post them. But the idea here is that this is one now Ethernet datagram ready to go. Now, how do we know that this is a fragment and not to be used as its own standalone bucket? Well, in the IP flags, in the header, there's a flags register, and there's a MF flag, which stands for more fragments. If that's 1, that means this is not a standalone packet. It has to have other stuff added to it. And when it also, there's an offset that says there are more flags, this is offset 1. Now the next packet doesn't have the UDP header in it because we've already taken care of that, but now we have the next 1480 bytes following that, and the reason that's 1480 because 1500 minus the 20 for the header is what remains. So this is the largest size we could have here. But notice now we have MF1 again, more flags or more fragments. Flag is set to 1 again, meaning there's another one after this one, and our offset here is 185. Now, why is that 185 when we had 1472? This is an offset it's in blocks of 8 bytes. So the offsets are always like blocks of 8-byte chunks of memory. So in other words, this would be offset 0 through offset 1485 in here. And now we're up to where this one's offset 185 for that one. The next fragment, 20 bytes, 48 bytes remain. So notice to send this 3,000 byte UDP datagram, we really had to send 3 IP packets across the network. Now, those get put back together in the right places using the offset, and it knows when it's at the last one, when it has the more fragments flag of 0. So this will say, all right, I had everything offset 0, I had everything at offset 185, everything starting at offset 370, and that's the last one. Now I put it back together in the entire UDP thing, and now I can release it to the system to be processed. But there is a problem with this, and that is if we allow fragmentation, then we have this potential problem. That since UDP has no mechanism for ensuring reliability or kind of the transfer logic where if a fragment gets lost or dropped, it gets re-requested. Essentially, any lost fragment will cause every one of the other fragments to be discarded. So in other words, if I had those 3 fragments and just that last one with the last 48 bytes got lost, let's go back and look at that for a second. So if this fragment gets lost, it'll dump all of it. It'll never release any of it to the system because it's an incomplete, it's a partial UDP packet. It can't release it. It won't re-request it, so it'll just dump it. And notice that problem gets worse the larger the UDP packet size is. So any lost fragment will cause all of the entire message to be discarded. Now, notice if we did make a maximum size UDP datagram, 65507, that'll end up being 45 of these fragments. So in other words, we'll have 45 of these, and the odds of losing one of those becomes higher the more of them there are. If we lose just one of those, the entire thing gets dumped. So let's say we lose 1 out of 45 fragments, all 44 of them that we did receive get trashed. They just get discarded. Now, the more fragments we have, the farther the network distance, the more likely it is that we'll lose one. And so we also have no way of knowing that message got lost. So the idea here is that can be a problem for us. So we want to try to avoid large UDP datagrams. And whenever possible, we want to limit the game server datagrams that we're sending to kind of that maximum size of 1476 bytes. So if we go over that, we have to fragment. If we're under that, chances are we don't have to fragment, so we're good. All right, so let's dig into the programming side of things a little bit here. So looking at programming for UDP, we've got essentially very similar to how we do programming in TCP, but there are some key differences that make UDP programming, at least getting it set up, simpler. First off, when we create a socket, we still use the socket function. We still use address family inet, but now we use sock_dgram. Remember with TCP we use sock_stream. Now we use sock_dgram instead. So that's the only difference with how we create the socket. Now sending data is different. First off, we don't have to ever call connect because we're not creating a connection to stream data through. In other words, we basically just have to drop data into the network, and we use send to function rather than send to do that. And the way that function works, this isn't the full man page for it. We're not going to do that right now. Let's look at that. As we say, send on this socket the data that's at this address. Here's how much of data there is. This is in bytes. So this is going to be a pointer to the data. This is how much data is at that address. The flags there are some flags associated with that we're not going to talk about right now. But then here's the address that we want to send it to, and here's the length of that address. So in other words, we're saying send this data using this socket to that address. Very simple. So in other words, this is just saying drop this letter into put this address on this letter and drop it in that socket to be mailed. All right, receiving data is also different and also easier. Remember with TCP we had to listen on that socket for incoming connections. We then had to accept them when they came in, and then we had our connection. But again, there are no connections with this. So what we do with receiving data is we just call this receive from. function. So we call send to send, we call receive from to receive. And notice that it pretty much works the same way, that we say, hey, receive a packet on this socket if it's available, or a datagram on this socket if it's available. When it comes in, put it into this buffer. Here's the size of the buffer so we don't overrun it. Now the packet that comes in, this doesn't have to exactly match the size of that. This could just be large enough to handle whatever would come in. And there's flags again, and then this is going to get filled in with the remote address of who put the data into there. So in other words, this is like pull a letter out of my mailbox, read it into the contents of it into this buffer, and then read the address off of the outside of the letter into this place here. So we can see the address and the port of who sent us that letter. Now, note that setting up the client is much easier in TCP in many ways because we don't have connections to worry about. We just have to create a socket and either send to on that socket or receive from that socket. Now, let's look at the programming needed for each, the client side and the server side. So let's start off with the client side here. So on the client side, we have this concept of what do we want to do on the client side? Well, we need to create a socket, and that's going to be, again, sock dgram, same address family, internet address family. And then we're going to fill in the address and port of the destination into an address structure. And then we're going to use send to send data, receive from to receive data, and then we're going to use close socket when we're done, or close or shut down if we're in Unix. But notice that there is no calling of connect anywhere here. We just create the address and we send to using that address. If we want to pull data back from that, we use receive from to get data back from it. So that's kind of how the client's going to work. And what we're going to do in the data that we send, that's up to us and whatever game we're writing. We'll talk about that here in just a second. But the idea there, relatively simple compared to TCP. Now on the server side, it's the same thing. Create a socket, fill in the address and port for the server. The only difference here on the server is we have to bind that to an address socket so that data can come in from that. And so now that we have bound to that socket, that gives us a kind of a public facing port that is reserved for us to receive data on. And when that data comes in, we'll receive it with a receive from, and we'll use send to send stuff back out. And we can use close socket or close once we're done. Okay, so fairly simple. Again, no need to listen, no need to accept. We can ignore all of that. Okay, so a couple notes on transfer. The send to function, we call it, it puts the stuff out there on the network and it's done. But just because the function doesn't, or completed, doesn't mean that the data is received on the other end. So in other words, when we call send to and it returns to us, we don't know that they received the data or not because UDP is unreliable. The receive from, however, will block and wait for a datagram to arrive. So in other words, if we call receive from and there's nothing in the buffer, it'll stop and wait. Now, note that that could be a big problem for a game client or a game server. And why would that be? Why would that be a problem? Well, think about, we don't want to have the entire game simulation stop while we wait for one datagram to come in or wait for network traffic. Now, there might be games where you want that to happen. For example, you might think of something like a game, I don't know, like something like Jackbox, where you're waiting for them to give you an answer and you cannot continue in the game until you get your answer. But for the most part, with a real-time game, like a first-person shooter, we want to just get messages when they arrive, otherwise keep updating the simulation. We don't want all of the bullets and all the players to freeze if we don't get a datagram in a particular cycle of the game loop. So we want the simulation to continue, and we only really want to handle messages when data arrives. So how do we do that whenever I call receive from it blocks? Well, the answer is it's pretty simple. We're just going to set that socket that we're receiving data from to be what's called a non-blocking socket. And non-blocking means when I call that function, if there's no data, it'll immediately return. And if there is data, it'll give me the data. So it allows us to switch the socket to this non-blocking behavior. Now, how do we set sockets to non-blocking? Well, if we're on a Unix-based system, we use this function called fcontrol. which is kind of file control. But what we pass is the socket. We say we want to set this set a flag, and we want to set the non-block flag for that. And if that returns to us something other than -1, then it worked. If it returns -1, then something about this function call failed for some reason. Could be the socket doesn't exist, the socket hasn't been created. There could be a number of reasons, but note that if this gets through without hitting that -1, the socket is now not configured as non-blocking. In Windows, it's a very similar process, but we have to use a different function. We use this IO control socket function. Again, we pass the socket, we pass this flag, file IO non-blocking IO, and then we pass this mode 1, which sets that flag to 1. Kind of the same kind of thing. This is really kind of doing something very similar, just as a different function call name to do it. And again, if this returns something other than 0, it's an error. If it returns a 0, it succeeded. So a little bit different return value on those. But the idea is we now have a way to turn a UDP socket to non-blocking. So once the socket is set to non-blocking, a call to receive from will return something that's less than 0. That would usually, or returns a -1. That would usually indicate an error condition, but we could check to see if it's a real error or whether it's just that it would have blocked and returned because there was no data. And there's a slightly different way to do that in both Unix and Windows. So to do that in Unix, it'll return a -1 and it'll set this error no. There's actually an extra one there I need to edit out. It'll set the error no global variable to E again or E would block, depending on which variant of Unix you have. But if it sets it to either of those, then we know that everything's fine. There's just no data available. In Windows, it's the same thing. It'll return this kind of error code of -1. And if we call WSA get last error, it'll have the value WSA E would block. Notice that's the same kind of flag we had up here. And everything else is just fine. There's just no data. So in practice, what we could do in most cases just say, assume that the cause of the error of anything we're received from is less than or equal to 0, indicates a non-empty or non-existent packet. Because received from, remember if we go back, it returns the length. So if this returns a length of something that's negative or 0, that means there was no data that we received. There's a problem with that we didn't receive anything. And if we turn off blocking, then this length will only be -1 or 0 when there's a failure. Okay, so here's some source code snippet. This is not a full program, so you can't cut and paste this and compile it. But if you look at this, you'll notice that this is kind of outlines the idea of what we're going to be doing here. So here's this packet structure. And the packet structure here, essentially all I have, I'm going to use this to stick data information in about the packet that I received. So this is going to be the payload. It's going to go into this packet_data variable. And then I'm going to have the length of that I'm going to store, how much of this is actually viable data. And then I have who it came from and what port they were on. All right, so to do that, here's a while loop that's going to just process all of the packets that I have. So essentially what I'm going to do is I'm going to set up this sock address in that's going to receive things from whoever is going to connect to us. And when that data actually comes in, we're going to stick it into that packet data. So this line here essentially says from this socket, which I'm assuming here has already been opened prior to this. We're going to read data into the RX packet underscore data dot packet underscore data. That's the since that's a name of an array used by itself with no square brackets on it, that's going to evaluate as the address of this thing in memory. So the address of that RX packet, which we declared up here, it's packet underscore data field in that. We're putting the address of that in. And since that's a void pointer, doesn't matter what type it has, so we don't have to cast it or anything like that. But here we put the size of that thing in. Looks like I'm missing a parenthesis there for some reason. and then flags of 0, and then we say the sock address structures that we had, this from address. We're going to put that in, and then we're going to put the from length, and that's going to fill in all of these two things into that. Now, if we get bytes rx, the return value of that that's less than or equal to 0, we break. That means there are no packets available. So this is the kind of thing will be in a loop. It'll happen over and over. When we hit this, it'll read all of the packets that it can. It'll then fill in the rx packet address, fill in the port. And notice here I'm converting those using network to host long and network to host short to make sure to take the things that were the address and the port and put those in. And then I'm processing the packet in here. So in other words, this will just process all the packets that are available. We'll see code that does this again here in a little bit. All right. So in this case, we just need to decide how to put our data into that data portion of the packet to make it make sense with our game. And the easiest way to do that is to use some sort of method to kind of serialize the data or put the block of data in there that matches the game data. Now, there are a couple of options here that I'm quickly going to mention here. The first one is binary. And in binary, you could say, just here's a block of data in memory on my one machine. Pass the address of that into there and the size of that. And that would send a structure or an array of structures or some sort of block of data that we create in memory on our machine. We're passing that directly across the thing. So there's no encoding overhead. But there could be problems. For example, if the server is running on a architecture that has a, let's say, big endian architecture and the client is running on a little endian architecture, then suddenly the way the data is represented at a binary level could be different. So encoding the data is often useful to encode it in some way. But notice that with binary, you could say, here's the address of this structure. We receive that data, give it the address of a structure on the receive from, and it's like the structure on one machine was magically transported to the memory on the other machine without any overhead in encoding at all. Now, we could also, if we want to encode the data to account for architectural differences, we could come up with our own. It could be text-based or binary, but note that that's not standardized. So we could encode it ourselves using like comma delimited text files or something like that. But again, that's something that's not going to be standardized, and we would have to write the code that's standardized or that encodes that completely ourselves. Now, another method is to use Json, which is a standardized way of sending data. And JSON also has this advantage of being human readable. So when you send it over JSON, you could look at that packet and see the way the stuff is getting put together. But the JSON tends to be a little bit more verbose and a little bit longer than other methods, one of which we're going to look at here in just a second, called MsgPack. And what MsgPack is that's a compact kind of serialization format that was designed to be really fast and compact. In other words, if we encode stuff in JSON, we might get a large amount of data. In MsgPack, we're going to get about half or less of the amount of data of a JSON encoded object. But MsgPack is a binary format, so it's not human readable, but I don't know if we really care about the packets going across the network as being human readable. And so for game data, I like MsgPack. It's also language agnostic. It's not, for example, like JSON was designed for JavaScript, but it's used in a lot of languages. MsgPack was designed to be kind of cross-language compatible, cross-platform compatible, and so we don't really need to worry about it supporting a server written in C with a client written in JavaScript, or a server written in C and a client written in C#. So MsgPack is a really useful kind of serialization format for compact, fast transfer of data. Now, also I've seen XML used. I don't like XML particularly for game data because even though it allows complex data to be stored, it's not compact at all. It's very verbose, much worse than JSON, way, way worse than MsgPack. and it's really slow to parse because it's a fairly complex format. That parsing XML files, even though there are libraries that will do that for us, is not a fast thing to do. Okay, now for our game server and demo, we're going to use Python. I'm going to use Python to look at this demo code. We could, if we wanted to, though, use C or C++, any language really, as long as it supports sockets. So what we're going to do is we've looked at C previously for how to do UDP. Let's look at how we would do that in Python. And the reason we're going to use Python for this is just the code is going to be a little more compact. We're going to get less bogged down in the weeds of data representation like we would in C. But one cool thing about this is you could write the server in C, the clients in Python, because the language we're speaking here is UDP. And if we use something cross-platform like MsgPack or JSON or our XML, or really any of these, except for the binary, then it doesn't really matter what language we write the code in. In fact, we could even still use binary and use Python struct module to deal with that. All right, so let's look at that Python program from both a client and a server perspective. We're going to start with the client. Okay, so starting with the client here, essentially we need to set up the socket, we need to know how to send, we need to know how to receive, and we need to then process the message that we received. So the idea here is pretty simple. All we have to do is import socket. To make the client socket, we just do socket.socket. We pass in socket.af_inet and socket.sock_dgram. So notice this is pretty close to how we did this in C. We just make one call to the socket, and then that creates the client socket. Now, after it's created, though, remember we wanted to set it to non-blocking. In Python to do that, we just say client socket.setBlocking 0. That sets it, or you could put false in there. That sets it to a non-blocking socket. Now, the next thing we're going to do is we're going to send messages to a server. We need to have the address of that server. So server address equal 127.0.0.1. Now, this is the local host, since I'm going to be running my server on the same machine as the client. So server and client are on the same machine. But I could, if I had my server on an IP address somewhere, I would just put the address in here. And the port that the server is going to be bound to, I'm going to put over here. And I just picked this kind of 12,000 here just randomly. Now, to send a message, we're basically going to do client socket.send_to. We put the message here. Now, notice that I'm encoding this message since Python's default way of representing strings in Python 3 is Unicode. I'm converting that to UTF-8 kind of single byte per character representation to send it, make it a little more compact. And I'm sending it to this address that I specified up here. In other words, to localhost on port 12,000. I'm sending a datagram. I'm addressing it to this. And this is the data that's in the payload. Just simple hello encoded in UTF-8. Now, on the receive side of things, I'm basically going to receive that message. And notice I put this in a try except. And the reason for that is because if I set this to non-blocking and I tried to receive from it, if there is no data, it would raise this exception. So what I'm doing is saying, in this try except, I'm saying, hey, get the message and address when I receive from, and this is the size of data that I want, maximum size of data I want to be able to receive from that. And it doesn't have to match that. In this case, it's not going to. We only have these kind of few characters up here to make up the message hello. But I just passed it the maximum size there. And it's going to get that message, which isn't necessarily going to be that size. And it's going to get the address of who it came from. In this case, it's going to be the server who sent it to me. Now, notice if the exception happens and I didn't receive a message, so I'm setting the message to none, the address to none. And then down here, if I'm saying if the message I got was not none, then I got a real message, then I'm going to process this. I'm going to pass that off to now be processed by my client code. So this is kind of the heart of how we're going to set this up. But we're going to have this stuff happening in a loop. Whenever we want to send a message, we're going to send it. We're going to check to see if there is a message. If there is one, process it. And then we're going to continue this part of the loop. But the setup of the socket only has to happen once before we get started in our main game loop. Okay, now the server side is going to be pretty much the same. Notice that this code is all really exactly the same, except the server address. I basically just used a blank to use. Like we could put localhost in there if we wanted to. But if you set that blank, it'll use whatever the local machine is. And then I had this one extra step of having to bind that socket to that address. And that's really just binding it to that port, making sure that port can now receive incoming connections for UDP packets. Now, on this end, I just did the receive first. I could do then process the message that was received and then send a message back out to the client. Now, notice one thing that's different about this is that address here came from the client. So when a client connected to me and sent me a message, I captured their address. I'm not using server ADDR, I'm using address. And then that's who I'm sending the message back to. So in other words, I'm sending the message back to whoever sent the message to me. And since that includes the port and address of whoever sent it to me, I'm going to kind of talk right back to whoever just talked to me. So whoever sent me, whoever I received the message from, I'm going to talk right back to them. Okay, now, the only thing we really need to do now is decide on a protocol for our game server. In other words, with that game server, how do we set that protocol up? In other words, what events come from the client to the server? How do I use those messages to then update the game state that the server is keeping track of? And then I need to send that data back out to the client so they can then render their screen. And then we're going to repeat that process over and over again. So in other words, client player does something, send that to the server, server updates the game state, sends the game state back out. And that sending of the game state back out to the players is going to be something that's going to happen really, really quickly and repeatedly. And one of the things to note here is the server is also going to need to have a way for players to join, a way for players to kind of exit when they're done. And the server is also going to have to keep track of who's all joined right now, because as it updates the game state, it has to send that out to every one of the players on our client list. So if we have 5 players playing right now, the game state changes. We need to say send this to client 1, client 2, client 3, client 4, client 5, so they all have access to the same game state. All right, so both the client messages and the game state will need to be encoded in some way. So we're going to need to get events from the client, send game state to the server. We're going to need to encode those. So we could use any one of those methods we talked about earlier. There's one more I didn't mention, pickle, which is Python specific, we could use. But I'm going to go ahead and use MsgPack mainly because it's compact, much more compact than these other ones, except for maybe struct.pack. And it's fast and it's language independent. So in other words, you could use this between different languages. All right, so we'll get to that in a second. So here's what we're going to build. We're going to have a game client, and the loop there is essentially going to look like this. Get user input, so like key presses, key releases, things like that. We're going to encode those in some way and send those in a UDP packet to the server. If data arrives from the server, then we're going to receive that game state packet. We're going to process the game state packet to update any local variables that we have. Then we're going to render it, and we're going to repeat that. So get input. If we get input, send a packet to the server. If a packet arrives from the server, then process the packet and render the screen and repeat that. On the client side, we're going to kind of receive client events. If we receive a client joined event, we're going to add an entry to our client table saying, hey, this person is now playing the game. If somebody leaves, we're going to get that client exit event. We're going to remove them from the table. Other than that, we're going to process any other events of this client pressed this key, this client pressed this key, this client made this choice, this client fired their gun, whatever, moved the mouse. It could be mouse, could be keys, but we're going to process those events. And then we're going to update the game variables, the game state, via simulation. Say this bullet now moved to this position. This player, because they pressed this key, is now moving in this direction. So we're going to update the entire simulation, and then we're going to send that out, loop through all of the people in the client table, loop out and send the new game state after this step of the simulation to everybody, and then repeat that. Get client events. If a client joins or exits, we update the table. We process all the other events, update the simulation, send out the new state to all the things. Now, there are some problems we should consider when we go to set this up. First off, UDP is based on just datagrams, so we have some potential for things that could go wrong. And those potential problems are an event could get lost. So if somebody presses a key and we send a single key press event, that could potentially get lost, meaning that we might miss the fact they pressed that key. Or it could be the other way. It could be they release a key and that event gets lost. So they're pressing a key to run through the map and they let go of it. They might keep running through the map if that gets lost. So we got to be careful about events being lost or possibly received out of order. They press and release really quickly. It could be received in the other order of release and then press, which has a different effect in the game. So we got to be careful about that. The other thing that we have is that game state responses coming from the server could get lost or received out of order. And lost isn't necessarily such a big deal in this because we're constantly streaming those out. But out of order could be. So if we get the game state packets out of order, suddenly bullets jump back in time for a frame, then they jump forward. So we might have a bullet that's moving like this across the screen, and then suddenly it jumps back here, and then it jumps back forward and then continues on its way. That could create problems for the user experience, and it could create problems for how the user perceives that game. So we got to watch out for that. Also, we have to think about all the kinds of events that could be sent, and they could be sent at the same time. Like you might press two keys at once, or you might press a key and a mouse at once. So we need to think about how can we send more than one event together, potentially. Also, the game state updates need to be sent repeatedly. So in other words, we're going to have to, every time through the server's loop, say update everybody with a new game state. New game state, update everybody. New game state, update everybody. So that's going to be the limit of how quickly we can get the data out to everybody. And notice that if the game state gets really large, we might have to use multiple fragments or divide it up ourselves, which is usually a better option than using fragments, into multiple kinds of datagrams. So here's part 1, update these things. Here's part 2, update these things. And the updates should be as quick as possible, meaning that there's a really large benefit to us getting the game state down as small as possible because we're sending that to everybody. Okay, so to make the protocol, we need to pin down those protocol messages. So in our case, we're going to do something relatively simple here. We're just going to do this kind of a key down, key up, join, exit, and then a keep alive. And the purpose of a keep alive is if we're not pressing keys, we don't want the server to assume that we have dropped our connection. So we might want to still periodically say, hey, I'm here, but I don't have any new input for you. And then that way, that'll allow the server to players that become inactive or drop off the game. It can kind of garbage collect those and get rid of them if they haven't responded for a certain amount of time. So you might make a keep alive message that goes through, hey, I don't know, 5 times a second if no other input. If no input has been made in a 1/5 of a second, go ahead and send a keep alive message just to tell the server, hey, we're here, we're just not doing anything right now. Now, server to client, the message there, we might need to send the list of all the players and their locations and speeds and health, and might include other things like their direction of travel. It could include things like their colors to draw them in, whatever we need to send here. And then the bullet list, that's going to be the list of bullets, or if there are bullets, that's where they are on the screen. Then there might be some items on the screen, like health boxes or something like that. We would need to pass those in. Treasures, I don't know, whatever other things we want. And there could be other data that we need to share as well. Now, one thing that's important to note is that if you have a game with something like particle effects that make it look better, there's generally not a reason to send the positions of all of the particles to every user unless the particles are involved in gameplay in some way. So in other words, if particles are just there for like visual effects, like something blows up and it makes sparks, you can just simulate that on the client end and make it create particles, even if they're created randomly and even if they don't look exactly the same on everybody's machine. That would still probably be okay to render those and only have those dealt with on the client side, rather than saying, hey, here's 10,000 particles that make this explosion. Let's send all of those along with us. If they're not critical to the gameplay, just have them be a visual effect on the client. But this is things that we can interact with usually we definitely need to send. Here's player 1 is in this XY, maybe XYZ location. Here's player 2 is in this location. Here's how fast they're moving. Here's the angle they're facing. Here's the color they are. Here's what their health is. Here's their name. So maybe you have it show up above them on the screen, like a little call out above their head saying this is player 1. And then anywhere interactable things, bullets that could hit players, any other items. So things we can interact with, weapons, health kits, whatever. Now, that's the kind of messages we want to create and send. And notice that these things are lists of data that we need to send. Okay, so a couple things to consider here is that we need to plan for our protocol to handle lost packets, lost event packets. So imagine a key press event getting lost or a key release event getting lost. Also, we should plan for out-of-sequence packets. Imagine the press and release being reversed. So we release and press instead of press and release. That can happen. So we need to be careful about that. And we'll talk about how we might be careful about that in a second. We might also want to plan for lost or delayed game state packets. So we might imagine some delays in the action happening. So if we lose game state for a certain amount of time, everything would freeze, and then when it comes back, everything would jump to some other place in the game. Now, there are ways to handle that as well that we'll talk about in a second. We might plan for out-of-sequence game state packets. Imagine a glitch. Again, the bullet moving across the screen jumps back, jumps forward, and that would be very strange for the user playing that to see everything jump back in time and then jump forward again. We'll talk about how to deal with that a little bit. All right, plans for users just dropping out. So user's network goes down, they're playing the game, their player freezes on the screen for a while. We don't want them there forever. We want them, maybe they take some damage and they eventually die, but we want to say, oh, they've left the game when we don't get a message for a certain amount of time. And then also might imagine a case where we do have some packets that might need to be acknowledged. In other words, there might be certain kinds of messages that are important that we do need to acknowledge. If we want to do that, we have to build it ourselves. Now, before we get into this any further, let's talk about some ways we handle these things. So planning for lost event packets. One way to deal with that is rather than having kind of lost event packets where we have a key down event and then a key up event, we could send a key state list that we send repeatedly. In other words, that's going to constantly say, here's what's pressed, here's what's not, and we send that over and over. And that could be part of like a keep alive packet saying, hey, I'm here, and here's the state of the keyboard. I'm here, here's the state of the keyboard right now. But if we send an individual event for this got lost, or this was pressed and this was released, and we lose either one of those, we now have something not moving when it should be or moving when it shouldn't be, and both of those would be bad. So thinking about the events as maybe we send a key state of all of the keys over and over and over again as part of our keep alive message, maybe that would be better. Also notice if we send just the current key state, notice that the out of sequence event packets become less problematic, especially if we throw away things that are not in expected sequence. But in order to do that, we need to add our own sequence number. And that's a good thing to do as well. That would also handle the out-of-sequence game state packets. In other words, if I just got packet number 100, and then the next one I get is 99, I just ignore that one and say, that's not what I'm expecting as a number, that's less. Now, if I get 101, I process that. If I get 102, I process that. So I only would ever process packets that are later in the game. There's no reason to go back and deal with things backwards. That's not necessarily true. We could set it up so that if something happened back in time, we go back and look at the simulation, the state that it was at that time. And if that would have changed the outcome, then we change the outcome of where we are now. And there are game servers that do that. And as far as planning for users dropping out, a keep alive will handle that just fine. And as far as some packets needing to be acknowledged, there are some really clever ways of doing that, where if every event packet that comes in has a sequence number, we can actually, and we're constantly sending out game state data, we can include a little acknowledgement field in the game state data that says, I got these previous packets from you. And there's a really clever method of doing that that I've used that I like, and that is to provide kind of this acknowledgement of packets looking backwards into the past. That one of the things in games, if the packet is too old, we don't want to really worry about it anymore. So it happened back in time, we don't want to worry about it. But if you think about a game running at, I don't know, let's say 30 frames per second on the network side, that 30 frames per second, if something happened like 60 frames ago, it's like 2 seconds in the past, who cares? We just ignore that. But things in the last, I don't know, tenth of a second might matter. But what you could do is you can create this bit field that says, this is acknowledging the previous packet. This is the one before that. This is the one before that. And since those are flags, either yes, I got it, or no, I didn't. So if I have a bit field that's all filled in with ones, that would mean I got every one of those packets. But if I'm missing 1, 2 ago, that means, hey, I got your packet sequence this time, but not the last one, but I got the previous ones before that. So that can give us this really clever way of having what would be called kind of redundant acknowledgments in a really compact space. Because if you imagine you just use like a 32-bit number, you're looking with 30 frames per second over a second into the past of acknowledgments, and you're going to keep sending those over and over again. So even if we miss one of the game state packets, if that gets dropped, there'll be another one that comes shortly after it acknowledging those same packets. All right, now we're not going to implement all of this right now. I just want to get a basic thing up and running. So let's go ahead and take a look at some code. So I'm going to pause this for a second, get switched over to code. I'll pause this for a second. I'll get switched over to code, and then we are going to take a look at how that code works. So let me get the code pulled up on the screen, and then we'll switch over to that. Okay, now we're back, and what I did is I basically pulled up a simple UDP game server, client and server. I've got the client here on the left. I've got the server code here on the right. And you'll notice that these are going to be similar in some ways and different in others. So let's start on the client. So one thing to note, that there are numerous problems with the implementation as it stands right now. For example, right now, there are no kind of keep alive messages. In other words, there's nothing that says when I'm not making moves on the client side, right now, there's no keep alive. Also notice the event system datagrams could be lost. They could arrive out of order. I'm not really handling any of that right now. And there's only one datagram handled per loop iteration. In other words, the client is basically sending one message per loop iteration, and there's no client-side prediction. And client-side prediction isn't something we really talked about, but that's something where the game frame rates on a local machine might exceed. We might want the game to update the frame rate, I don't know, like 120 hertz, but the network code doesn't need to do that. But the problem would be if the network code is running at 30 hertz and the game is running at 120, any network elements are going to look choppy and kind of like jittery as they move across the screen, and we don't want that. Well, the way we could handle that is by, on the client side, we could make it predictive, so it knows the rate at which things are moving, and even if I don't get a new network packet, I can kind of draw it in the it's almost like interpolation of the motion of things. And then when I do get a message from the server that puts it at some place other than where my prediction was, then I correct for that and then do that. And actually that correction for where it came in on the server doesn't have to be instantaneous to make it look like it jumps. We could actually blend those things together over time. So we predicted that the trajectory was like this. It was actually like this in the server. It should be up here. So rather than jumping it up there, we'll move it towards that so that the next time we're more accurate. And that can make a better user experience. But the idea is on the server is the definitive decider on who takes damage and who's where. But to make the client experience look smoother and better, we can do prediction on the client side. Now, we're not going to get into all of those fixes today. Let's just basically look at the basic code here. Okay, so the first thing that I have here is here's my client. And this is going to be a really simple game with just a kind of a face moving around on the screen. But on the client side, I basically keep track of the player's X, their Y, their name, the size, which is they're going to be their radius, their speed, and then the color that we're going to use for them. Now I've created these two methods here, one called dumps and one called loads, and that's to allow us to kind of create the data that's representing this client that's going to be sent across to the other side or received. So dumps is actually taking all of the attributes of this that we want to encode, putting them into a dictionary, and since dictionaries are something that MsgPack can very easily dump into kind of this encoded string format or byte array format, what we're doing is we're just saying take that thing, use MsgPack to encode this dictionary that has the X, the Y, the name, the size, and the color. Again, X, Y, name, size, color. Notice in this case I'm not really using speed in there. I could add speed in there. And then loads does the opposite. It says, here's from MsgPack, take this in string that came in and unpack it. So loads unpacks things from message. And then it makes a dictionary of that. So here I am putting the things back into the attributes. So this is essentially taking the attributes and encoding them. This is taking the attributes and assigning them based on what we decoded from that. So we now have a way to have this object have things sent across the network for where it is, and then pulled back from the network from when we got the response. Now, renders just draws a circle on the screen to show where the thing is. Okay, so continuing on in that code, let's get to the actual network part of this. Now, for processing network messages, I made two functions. I made one here that basically sends a network message. We pass a message to it. It sends it. And what happens really behind the scenes here is I have this client socket.send_to, and I send it to the address of the server that was configured, just like we did before in code we had before. Now, one thing that's really useful is here is some code to simulate lost packets. And that can be really useful for testing purposes, because if you're testing on a local machine, on localhost, you're not going to lose any packets. But once you get, so you could have something that works great on the local machine, and then you try using it on the internet, and suddenly everything is broken. So one of the things that I like to do in my test code for network setups is to kind of simulate losing packets by doing something like this. So here I'm just generating a random number between 1 and 100, and I'm saying if it's less than or equal to 10, kind of a 1 in 10 chance, then don't perform the send, just skip that send. So this will simulate the possibility of losing packets. And you can actually up this amount if you wanted to. So you could say lose 50% of the packets and see how the system performs. Lose 1% and see how it performs. So you could very easily simulate how your program, your game server will perform, or your networked game system will perform under varying network conditions. Okay, down here I have this getNetMessage function, which what it does is just tries to get a message. If it gets one, it returns it and the address it came from. If it doesn't get one, it returns none for both of those things. So we saw this code before previous as well. Now, to process the message, notice what I'm doing here is I'm basically saying go through the player list string and unpack that from the message that we received. So the message we received is going to be our game state. In this case, I'm just getting the player list, and I'm going through for every player in my player list string that I had up here, because this, when it unpacks that, it's going to get all the player list back. Then what I'm going to do, create a new player, and then append that to the list. So I clear out the current player list I had, update it with this game state that I just received. So in other words, I don't have a bullet list, but the bullet list would work the same as what we have here. This is just the player list. We're going to get all of the player data. We're going to fill all that in and do all that. Now let's look at the main part of the code down here for the client. Initialization, the part we're concerned with, this is just going to use Pygame to do some simple stuff to show this. But down here, we open the socket. We set the socket to non-blocking, and we set the server address that we're going to connect to as localhost port 12,000. Now we're going to send our join message, and notice I'm calling my send net message function, and the message I'm creating to join is going to be join, and then the player name in this case is going to be Paul. And I've just created this string message to encode that we're going to join. So the thing before the colon is the kind of event type. The thing after the colon is the data that goes with it. So I'm saying join, and here's the name I'm joining as. Now after that, we just go into our main loop, our game loop, and the game loop basically says get keyboard events from the player. If one of the events is a key down, then go ahead and send a KD, key down event, and send what key it was that they pressed. So I'll just send the key to the server. If it's a key up event, I'll send a KU event to the server. So again, I'm just forming these message types as right now we have join, we have KD, we have KU. And now here, what we're going to do is we're going to loop to process all of the messages that are currently pending. So to process all the messages that are pending, I basically call my getNetMessage function. And if what I received back was not none, that means I have event. I call my processNetMessage up there. And remember what that did is that just pulled all of the things out, replaced my player list with the player list I received. So getting the game state and updating it. And down here, I just go through and update the player list, which was just received by this. If I got a new one, and I rendered that to the screen and then update. And then if I'm done with this game, which the only way I can get out of this right now is press escape, I send this net message quit to the other end to disconnect. All right, so that's it for the client. Relatively small amount of code here. And simple, we don't have bullets, we just have a list of players. But on this end, for the UDP server side, it's really not any more complicated. The only difference here is I still have the same stuff here that I had down there. Except for I need to keep track of, for each player, I need to keep track of what IP address they connected from and what port they connected from. Because when I talk back to them, I need to know that, who talked to me in order to talk back to them. And down here, this keys down, I'm going to maintain a key state for the client to know what key is currently pressed and which one's released. So these three things we've added here. Now in move here, I'm going to say if A is in their keys down, then I update their position based on their speed. If D is W, so WASD I've defined. And then I make sure they can't leave the screen here. Get net message, send net message, pretty much work the same as they did before. Notice that you could add code to randomly simulate random loss packets here on the server side as well. Now, over here, process net message is a little more complex in that I'm saying, hey, if the first character, if it's one of those things in a tag, then I'm going to cut the rest of it out. And if there's a colon in it, then I'm going to split the data based on that colon, divide it into a command and a data part of that message. If there's not a colon in there, then it's just the message. And now I check the command. If the command was join, then the player gets added to the list of players. And notice here I'm adding them. I'm saying player list str address is player that. So in other words, I add this is actually adding a dictionary entry for that player. Could be a table, but dictionary is kind of a table, so we'll add it that way. And then if they quit, then I remove the player from that dictionary. If they press KD, then I go through and I update which keys are pressed down. If it's KU, then I update their thing and remove that key from their list of what keys are currently pressed. And that's it. And then the last thing I have is the player list.dumps, which takes all of the players. This is the game state. I return that. And so now in my main program, everything's set up the same except I have to bind. So I'm ready on port 12,000 to receive that message. And down here in the game loop on the server, it's very similar to the other one, except that notice what I have to do here is, first off, I don't have any local keys here to move up, down, left, and right. That's all coming from the things. But what I do is I process all of the events down here. I then update the game state by going through all the players and moving all of the players based on what keys were pressed. That move function looked at that. So I'm going through the player list dictionary, updating every player. So if they're all moving, they've all pressed keys, they move to a new location on the screen. We send that through to all. We then send that to all of the clients. So we get the game state here, send it to every one of the clients, clear the screen, and then we render it on the server just so we can see it. So we don't really even necessarily have to do any of this rendering stuff or even have Pygame at all. But in this case, it's going to be useful to take a look at that and see those things moving around. Okay, so let's try this and see what happens. And notice that I am going to go ahead and leave in the simulation of lost events, 1 in 10 chance of losing events over. All right, so let's run the server first. All right, so there's the server. Windows wants me to allow it to have access to bind to that port, which I did. So here's the server. Let me make this smaller and put this over here with the server so we can see the messages coming in. So notice it says the server is running. Okay, so that's the server. And notice I did change the caption so we can see that the server is running. Nothing has joined right now. Now let's come over here and let's run the client. And let me make this smaller so we can see the client messages. Oh my God, they got like a 1 pixel. Okay. Ugh, that's not what I wanted. Client. Client. Okay. All right, so here's the client over on this side. There's the server there. Now notice I joined, and when I ran this, it automatically joined. Down here, added player to player list, Paul from that location. And notice this port, 62,400, that was one that was automatically picked for us. But this is the one that this is going to receive messages on. And notice that we have to be receiving that message because we're seeing the player there. So I'm going to go ahead and click on the client screen up here and move the client around. And you'll notice that on the server, it's getting that. But we do have that 1 in 10 chance. So I just let off, and we're still stuck now because we lost the key up message. So I'm just going to press D and release it here. Oh, it missed the key down there. Missed another one. And now it missed the key up. So notice that we have not handled anything about, and that key up, A key is basically stuck now. So even if I press D, it's not undoing that. Oh, now it missed another key message. So I have to press A and release it, and now I'm back to it working normally. But one of the things you'll notice is, oh, D is stuck now. So again, adding that little bit of code in there to simulate losing packets can be really useful for seeing how your system works under degraded network conditions. And that's really important for UDP because you are going to lose packets. And if you're on localhost doing your testing all on a localhost or even a local network on a LAN, you might not see very many lost datagrams. But fortunately, we can simulate that behavior and see what happens. Now, so that's the first attempt at this. Notice we are using MsgPack. This thing is moving around, but we have that lost kind of thing. So let's look at a different version of these programs. And notice when I exited, it says it removed it from the list. So all of that works great. But let's look at a slightly different version of this. Let me pause this. Actually, I might be able to bring them up in here. Let's see if I can just do it from here. Yeah, let's just go straight to 3 here. So this is the server side. All right, that didn't work how I wanted. And client. Client 3. Let's get rid of this guy. Okay. Now this version is going to be a little bit improved from the last one. Actually, I should have gone to version 2 before going to version 3. Let me do that. I'll leave these up and I'll go and open client 2. Stick that on this side. Let me open client or server 2. And stick that on this side. Okay, so what this version does is it sends the game state as a dictionary that includes the list of player dictionaries rather than doing the encoding the way that we did it before. And notice the other thing that has this game state dictionary that's a global, player list that's a global. And what this is doing is this allows us to add additional things to that dictionary. So in other words, we could add a bullet list to the game state dictionary. We could add have the player list is already in there. We could add object entity lists to that dictionary. And because MsgPack is very good at packing and unpacking dictionaries, including dictionaries that have other dictionaries or lists of dictionaries inside them, then we can really just put everything into the game state dictionary and send the whole thing. The other thing to notice about this is I'm still doing the key down and key up. I'm going to kind of keep that even though that has created problems for us. But notice that this is now setting us up to send more complex data, which means that on the server side, I could fire bullets and just stick those things into that, the game state. Let's get to the part where it puts the game state together here. Okay, create list of player dictionaries. So player dictionary list, I go through this and I get the basically do player dictionary list out append, active player dictionary, and then I stick that and call the dumps on that. So it's going to dump all of those. It's creating a list of dictionaries that I'm sending to the other end. And notice that that could be really useful. We could take that list of dictionaries and then we're going to add that to this game state dictionary under the key player dict list. And so this has all of the players' dictionaries inside of this one list under this thing, and then we're encoding that whole thing. So this gives me the ability to now add other things to the game state dictionary. So for example, I'm not going to add this right now, but you could have game state dict, and then in here I could have bullet list I could do that equal, and then I could say put all the list of bullets in there, and that if I put that into that game state dictionary under that key, then I could extract all the bullets on this end from that key the same way, and MsgPack will handle that stuff just fine. So I'm not going to do bullets right now, but notice that we can now add, I'll put a comment here, so there's a little comment that we could easily add other things to that game state dictionary. So we have one data entity that we encode with MsgPack, and that one entity can hold a lot of different things inside of it. Here's the list of all the players, here's the list of all the bullets, here's the list of all the health boxes, here's the list of all the whatever else we want to add to that, and that will send all of that to the other end. Okay, let's go ahead and just try this this one as well. All right, so there's the server. I guess I just want to move this over here. So there's the server. Let's also run the client. There's the client. This time I drew a little face, and now you can see him kind of running around on the screen. And this would work over the network. And if another client were to join, I could have two of them in there moving around at the same time. And then version 3 of this, I added, kind of improves things a little bit further using struct.pack rather than using MsgPack for everything. But it's really basically the same thing. Now notice there are still some problems with this code. Let's switch over to version 3. Notice when I exited, it exited. We saw him exit. And notice that the server is still running, so I could rejoin. Let's run that again. We rejoin. He has a different color. Now he shows up. So notice we have the server and the client talking to each other just fine. All right, so let's exit out of there. Let's exit out of the server. Server is shut down. but notice that we got a different port the second time we connected than the first time. And these are kind of auto-assigned by the operating system. But remember, they get passed through to the server so it knows who to respond to. All right, so let's look at version 3 now. In version 3, what it did is it used struct to encode the player data rather than using other things. So notice here, this is going to be much more compact in a binary format. So in this case, notice what the struct module does. I just imported it, import struct. But the way struct works is it allows me to kind of encode this data in a more compact way. So I have a load struct and dump struct. So to dump the struct, I basically say encode it as HHHHCCCC, and then a string that's 16 characters long. And this is called the struct format string used for packing. And HHHH, what H is that's essentially a unsigned short integer. C is an individual kind of character value, single bytes, and 16S is the 16 bytes of a string. So notice what I'm putting is in is the X position, so that's X. The Y position, that's Y. And let me scroll over here and we can see the rest of this. And then I'm putting in the size, which is also an H. But then I have this byte array that's the color. Notice I have color 0, color 1, color 2. Those are the three C here. And then 16S, so 16 bytes, and that's going to be the name. So over here, that's just going to be, this bytes self.name encoding. So this is packing the stuff in ourselves in our own structure format, how we want it to be. And notice in this case, this is going to be 2 bytes, 2 bytes, 2 bytes. So that's 6, 7, 8, 9, plus 16. So 25 bytes worth of data that we're packing this into. So very compact, very small. And then unloading it the other way, we basically do unpack instead of pack. And then that's going to pull it back out into the X, the Y, the size, the RGB, the name, and we just put those back into the thing. So very similar to that, but more efficient with data usage on the packet because we're struct packing it in a kind of a custom way there. Rest of the code works the same. All right, so let's run the dictionary, or run the server. So there's the server running. Minimize that. Let's run the client. There's the client. And notice kind of same behavior with this moving around and being tracked on the other end. In fact, on this one, let's run one additional instance of this client. Let me see if I can do that real quick here. This is client 3. Let me double click that. Okay, and now notice I have 2 clients. And notice it handled that just fine. So here's client 1. The purple one is the top one, green one's the bottom one. And notice that if these were on different machines, on different parts of the internet moving around, they could both be moving around simultaneously. Unfortunately, on Windows here, I can't really click on both of them at the same time. And one cool concept, though, is that you could write a client that joins and runs as a non-player character. So, for example, I can make one of these that moves around on its own. Now, notice there are some improvements to be made here. We've kind of reached my time limit of how far I want to go on this. We're almost at an hour and 20, coming up on an hour and a half. But one of the things that would be a useful improvement here would be to do the client-side prediction. So right now things are performing pretty well because we're on the same machine. We don't have internet delays and latency there. But if I were to run this on the internet, it might across the other side of the world, clearly we'd have some slowdown here, and we might want to do client-side prediction. The other thing is, notice I'm not handling the key state very well. In fact, the only reason this is not losing messages like the first one is I commented out the code that was purposefully dropping packets and testing that. And since we're on the local machine, we're not really going to lose any packets. So we would need to do something different about the key state and verifying the integrity of the game state. We also don't have any sequence numbers in here, but that's actually really easy to add to this version, because we could just, in our game state dictionary, add a sequence number. And if the sequence number we got is less than or equal to the one that we got previously, we just throw that packet out, don't process it. And so that could be really, or at least don't get the game state data out of it. All right, and so this is this as it's written now could handle a large number of clients. One other thing we might want to do is limit how many clients we can handle at one time. So right now this doesn't have any bounds on it, so we could have hundreds or thousands of these clients, but it's going to slow things down because remember, on the server we've got to push out that message to every one of those clients, the game state to every one of them. And the larger the game state gets, the more time that takes. So we might want to limit the number of clients. Now, if we wanted to make a massively multiplayer game, rather than having one machine over here handling the game state and sending it out, we could actually have a cluster of machines handling that to have something like a massively multiplayer online game. But we could handle a lot like this. It would also help to optimize this code and write it in the language like something like C, or if you wanted to use Python, it would help to use some sort of optimization library like Numba in order to make the loop part of the code much faster. All right, let's go ahead and stop there. Notice when I exits just fine. When this guy exits, you'll see that guy exits from the server. So our game messages work fine. One thing to note, though, again, is that we are not acknowledging the join and leave messages, which could create a problem, that those could get lost as well. So we might need a way to add acknowledgments to this to make this a little more reliable. All right, so let's go back to the presentation for just a second here, and then we'll be done. All right, so we looked at the code, and really that's all that I wanted to get through today. But note that there are some of the things in this things to consider list here that we have not really dealt with. But that's all for today. Go ahead and stay safe, and I will see you next time. And next time, by the way, we have one lecture left. I am going to post a bonus lab to do game server stuff. But for the next lecture, I want to at least touch on the concept of WebSockets and do a little bit with that. But really, that's going to be our last lecture, and then we'll be done. So you'll have a week to work on the bonus lab or the other labs between the last lecture on Wednesday and then the final, which will be the following week according to the schedule. All right.